Okay, here we are. Hello, Hugh. Episode 297 of Space Nuts coming to you a couple of weeks early because Fred's hitting the road, so we're knocking one over ahead of time. So this one just will be put on the back burner until next week. I think that's the way it works, doesn't it, Fred?
It sounds good to me. Yep.
All right.
Week after next, we'll be back as usual.
And we're doing a live test. We're sort of preempting a live program leading into episode 300. So we're testing this. So it's possible and may already have a few people watching us on YouTube. I feel sorry for you. I mean, look at this. Why would you want to see it? Like the goatee, Fred. What's
good.
going on?
Yeah. It's nearly 2 weeks old now, Andrew.
Yeah.
It's so Marnie.
It takes minutes off your life.
It's what you get when you're a living fossil. And, I did it for Marnie actually, because there's a character in one of the series that we watched that she really liked who had a goatee, and she said, "I wonder what you'd look like with one." So
give it a go. I think it looks great. I like it.
Ah, thanks. That's good.
Works.
You're the first person who said that.
Well.
I do too, actually. I think you can never tell, until it gets a bit more robust.
See, I used to have a full beard when I was younger.
Yeah.
And that was fine. And then I shaved it off one day and played an awful joke on duty by shaving it off, putting on a trench coat and a hat and dark sunglasses. And I held a clipboard and I knocked on the door and she opened it and I said, "Hello." She slammed the door in my face. Then the kids let me in and she's saying, "He's a weirdo, don't let him in." And 20 years later, I thought I'll give it another go, but it came out in 10 different colors. I thought, nah, not doing it.
If you wait a few years, it'll be like mine, uniformly grey. That'll be fine.
Could be. It's starting.
Yeah.
It's starting there. Yeah.
Anyway,
my grandfather was grey, but my father, who's now 84, is not grey. So
good on him. Wow, that's pretty good.
Yeah, don't know what happened there, so I don't know which way I'll go. But I don't mind. I'm not that fussed. I don't mind what color it turns, as long as it's not green.
Yeah, green. Well, green's quite a popular color these days.
It is, yes. All righty, here we go, Hugh. Episode 297. Once again, we're having audio issues with the interface, so I'm going to do it the old-fashioned way. I'm going to use one of these. We'll see what happens. Oh, dear. All right, you ready to roll, Fred?
We're ready to roll, yeah.
Ready to roll. Okay, in 3, 2, 1. Hello again, and thank you for joining us on Space Nuts, where we talk all sorts of astronomy and space science, news from space agencies and astronomers and scientists and physicists, things that have been discovered, things that have been achieved, and we try to unravel some of the great mysteries of the universe. And we may have one of those solved today, perhaps. So whether you're at home or at work or sitting back in front of a lake fishing, whatever you're doing, thanks for joining us on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
It does indeed feel good to be here, and thank you for your company. As I said, my name is Andrew Dunkley. I am your host, and joining me, as he always does, without question, without claiming any money, without really thinking about it, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. Australia's living fossil.
Australia's living fossil, yes. Congratulations again on your honorary doctorate. And I've told a few people and they pass on their congratulations.
Oh, that's lovely. Thank you very much.
Good for you.
Thank you. Yeah.
And I know I said it sort of off stage, but loving the goatee.
Oh, good. Good. I'm glad to hear it, Andrew.
If you watch us on YouTube, you'll be able to pick that up. I think it suits you. That's very sporting.
My son, who I saw on Monday at the graduation, he's told me it makes me look exactly like my brother, who's one of these for 50 years or something. So,
well, it takes seconds off your age, I must say. All right. Now, today we've got a few things to talk about. This first story surprises me. Apollo samples that were collected 50 years ago, some of them were not opened until recently. Why would you bring them back and not open? I don't get that. And a particular black hole merger may have an explanation. We'll be looking into that. Plus, we have questions about the Thermi paradox. Mars, can we kickstart its core? That's a good question. And we do a follow-up on that light speed story or question we answered a few weeks ago about it slowing down in the vacuum of space if it goes into a glass tube and then speeding up again. Someone wants to know how that's possible. So we'll try and answer that for you, Greg. And whatever else happens, just happens. What happens in Space Nuts stays in Space Nuts, as they've never said before. But Fred, let's start off with this situation with Apollo samples, and they brought back quite a lot of stuff, and some of it just sort of sat there for 50 years, sealed, and I assume forgotten, or just we'll get to that at some stage. And it took them 50 years.
Yeah, at first sight, it does seem weird. I agree with you, but there is a very, very good explanation, and I think, it's brilliant reasoning. So I can't remember the number. I think it's about 380 kilograms altogether of rock and soil that the Apollo astronauts brought back with them in the 1960s and 70s. I do know, because I've got the number in front of me here, that it was a total of 2,196 samples.
Oh, wow.
Yeah. So it's, they had a fair number, and that wasn't really the reason why they've waited 50 years for some of them. The real reason, and it's really cunning stuff, it's forward thinking of the first order. The scientists who were interested in these moon rock samples 50 years ago knew that in 50 years' time, the technology to analyze them would have advanced out of sight compared with what there was in the 1960s and 70s. And
forward thinking.
Yeah. So they reserved, I think, probably 3.
Okay.
It's of which I think it's 3. There might be more actually, but one of them has now been opened, and that's why the news is big. It was actually Laurie Glaze of the director of the Planetary Science Division at NASA headquarters, who wrote in a statement that NASA knew that science and technology would evolve and allow scientists to study the material in new ways to address new questions in the future. Brilliant, isn't it? That's exactly what's happened. I'm not sure to what extent. I think things were pretty well advanced in the 1960s and 70s. So that's when I was beginning my career as a working scientist. But things have moved on just out of sight since then. If it's anything like the way we do astrophysics, planetary science has come on by leaps and bounds. So a tube of material, 35 centimeters long, 4 centimeters wide, which was hammered into the ground actually on the Apollo 17 mission, the last of the Apollo missions in December 1972. Gene Cernan and Harrison Schmitt were the 2 astronauts who walked on the moon.
Wasn't Harrison Schmitt a geologist?
I think you're right.
Yeah.
Yes, I think you're right.
I think he kept getting into trouble because he got so excited he was running out of oxygen, and they were saying, "Hurry up, hurry up!"
Yeah. So I think that's right. Yes, it's a mistake to send a geologist to the moon, isn't it?
I would think so.
It's just going to be like a kid in a lolly shop. Anyway, they kind of hammered the tube into the ground, pulled out the tube with rocks in it, and vacuumed and basically sealed it on the moon. And that is the way it's been kept for 50 years. So not only does it have rock in it, Andrew, but the volatiles that might be locked up in these rock surfaces, sort of things that are gaseous like carbon dioxide at normal temperature here on Earth, and things that are liquid like water at normal temperature here on Earth. So the the existence of these gases kind of locked up within the rocks, that there wouldn't be much, because of course the lunar surface is essentially a vacuum. But the idea is to, and I don't think this has been done yet. The idea, actually, no, the extraction has taken place. Sorry, Andrew. Anyway, the idea is to extract them and the minute quantities that are there, and analyze them with the technology that it's really about the precision rather than the ability to do it. This is spectrometry, so you're looking at the absolute fine details of what's going on in these atoms. Let me just check that you're still
And
there.
I did
Yes,
look.
you are.
You mentioned the weight of the material they brought back, which I think we talked about not so long ago. 842 pounds of stuff they brought back from the moon, which equates to 382 kilograms.
So I was out by 2 kilograms.
Oh, it's close enough. Round
Close
down.
enough. Rounded down, yeah, 382. And I had a feeling it was 380 thereabouts. Anyway, so the process has started back in fact last month, February the 23rd, as the venerable phys.org website tells us, because that's one of the places where this story has been carried. Scientists began a weeks-long process aimed at piercing the main tube and harvesting the gas contained inside. And then as over the coming weeks, they'll take the rock out as well, and they'll break it up so that it can be studied by several different teams. But what I really like about this sample is that it's not just any old sample, Andrew, because where it came from is where there was a landslide. And Julianne Gross, perhaps, Deputy Apollo Curator, is quoted as saying, "Now, we don't have rain on the moon, and so we don't quite understand how landslides happen on the moon." So that's a good point. And so some of the research is, is aimed at trying to understand how these rocks enable landslides to take place, what causes them. So moonquakes do exist, as we know. I guess that is a possibility. And so actually I was wrong there. I think there are 3 lunar samples still left after this one's been opened, which by the way is known as 73001. That's its name. And there are still 3 sealed lunar samples. So, the question is, Andrew, which I'm sure you and I would ask if we were there, when will they be opened? Is it going to be another 50 years? And we've got a nice quote from another senior curator, Ryan Ziegler. "I doubt we'll wait another 50 years, particularly once they get the Artemis samples back. It might be nice to do a direct comparison in real time between whatever's coming back from Artemis and with one of these remaining unopened sealed cores." So
the moon is once again drawing a lot of attention with, the Chinese are pottering around up there at the moment, and the Americans want to send in the next few months an Artemis rocket around the moon.
An orbiter.
That's the one we talked about last week, where you can put your name on a flash drive if you want to. And that's with a view to going back there with a manned mission or a human mission. Let's be politically correct. And they're talking about putting the first woman on the moon. They're talking about putting the first black person on the moon. And, this is all great. I think it's all fantastic stuff. And the moon being our closest neighbor in terms of what's out there, we should be giving it much more attention. There's so many possibilities. And of course, it will potentially be a great launch pad for missions beyond Earth and the moon going forward. So, learning everything about it, right down to the geology, not a bad idea. Not a bad idea.
It's going to be, the next decade is going to see our knowledge of the moon totally revolutionized, which is brilliant.
Yeah. Just wondering, though, this is a sort of one of my stupid brain questions. Would a landslide on the moon happen in slow motion compared to Earth?
It would, given that, walking happens in slow motion.
Yeah.
It would. Yeah. The acceleration due to gravity is lower on the moon, of course.
Because they did that experiment, I don't know which mission it was, where they dropped was it a hammer and a feather?
It is, yeah. And there's a movie.
And they
of
both
that.
fell at the same
That's
speed.
right, which is Galileo's.
Yeah. So I wondered if a
postulate.
landslide would.
Yeah, they
happen in
would.
slow
Well,
motion.
if you watch the clip of that, of the hammer and the feather, they kind of drift down.
Yes.
They don't.
They don't drop like they would on Earth.
Yeah, that's right. Yeah,
Interesting. Very interesting.
it's great stuff.
Yeah. More to learn from the moon, and lots of exciting things happening on and around the moon in the not too distant future. And that Artemis 1 mission is slated to launch sometime in the next few months. So, and as we mentioned last week, if you want to get your name on the flash drive that they're going to put on the Artemis 1 rocket so that you, or at least your name, gets to do a lap of the moon, you can jump on the NASA website and register. I've got my boarding pass. I'll send you a boarding pass. It's so cool. You're listening to and watching Space Nuts with Andrew Dunkley and Fred Watson. All right. I don't know if you heard the interference, but I just went on and to see if YouTube was working live.
All right.
Anyway, the idea is to extract them.
There it is. Yeah. Look at that.
Quantities that are there.
Yeah, so it's in a delay.
Yeah, I could hear this voice.
Yeah,
coming
that
from
was
you.
me. Sorry.
It's all right. I was worried something had gone wrong, but that's okay.
The ability to do it. This is spectrum.
But yeah, it's working. So hello, if you're I can tell who's watching. If you're watching live.
Nobody.
So you're looking at the absolute fine details.
We do have 5 people watching. Hello to you.
Wow. Welcome. Tune into Space Nuts.
Yes. This is a test. This is a test. We're testing for our 300th episode, just in case you wonder why we suddenly popped up live. But I suppose if you're a follower on YouTube, you'd get notifications
get a
of these live
notification, that's
things.
right,
So
yeah.
we don't mind. We do not mind at all. Okay, we're going to move on to topic 2. So people get to see what happens between segments, Fred. This is scary.
Yeah.
Like they get to know the real us. That's not a good thing. At least on my end. Okay, are you ready to roll?
Yes, all set to go.
Okay, here we go. In 3, 2, 1.
Roger, you're loud and clear here also.
Space Nuts.
Thanks for joining us. Always good to have your company, and hope you're well too. By the way, if you want to become a patron of our little program, you can do that via our website. Patrons are the people who put a few dollars in our bucket once a month. You can choose how you want to do it. You can do it through Patreon. You can do it through one of those other ones that I can't remember now. Gee, I love live radio. But it's as easy as jumping onto our website and doing so. PayPal it was. Or you can buy us a cup of coffee. There's just a button there, so you can just send us the value of a cup of coffee as a one-off. And a lot of people have been doing that. So if you want to become a patron or a donor, you can do so on spacenutspodcast.com or spacenuts.io. And if you don't want to do that, you can help us out another way by leaving reviews, whether you do that on YouTube or Apple Podcasts or Google Podcasts or any of the other podcast sites. Yes, leave us reviews. They help to get the word out and increase our audience. The more the merrier, I say. And thanks for your support, by the way. If you are a patron, we really do appreciate it. It enables us to do things like this. Make patches for our shirts. It's very important. Now, moving on to our next story. Black holes, one of the great mysteries of the universe. They are probably one of the most intriguing things that have ever been discovered and studied, and we still don't know a heck of a lot about them. And we get so many questions from people asking about black holes. What if it's this? What if it's that? I think this is what a black hole is. And last week, the question, what happens when a black hole dies? And the answer is, we don't know. But it could turn into a white hole. We don't know because they take a long time to drop off the twig, basically. The latest news on black holes is a particular black hole merger which they may now be able to explain. We do know they merge and they get bigger as a consequence of that. But there's one that's hit the headlines, courtesy of, is it the University of Copenhagen?
Yes, that's correct. That's their press release. And but it's work that's been done in Copenhagen as well as in the United States, in Oxford, and I think in Japan too.
Wow.
Maybe other nations. So this is a global collaboration, and that's often the case, Andrew, in work that involves the gravitational, the observation of gravitational waves. So this is results from LIGO, the Laser Interferometer Gravitational Wave Observatory, and that was the first instrument that was able to detect the gravitational signal of black holes merging. So these ripples that spread through space-time, not the gas in space or anything like that. It's space itself that's rippling when these giant gravitational phenomena take place. And gravitation and black hole mergers are among the biggest of those events. So this goes back to a particular gravitational wave event. I think you and I spoke not very long ago about the number of discoveries of gravitational wave events clicked over 90. It was either earlier this year or late last year. It was back in 2015 when it was number one. In fact, we didn't find out about it until 2016, but that was the first one. And now these things are, it's like almost like a factory, because LIGO as well has been joined by the Italian gravitational wave detector, which is called Virgo, and there are others too coming on stream. So the event in question took place in 2019. It is called GW190521, which suggests it occurred on the 21st of May 2019, which is what the numbers unscramble as. And it's a black hole merger. Sometimes these things are neutron star mergers. Sometimes they're black hole and a neutron. And you can tell the difference between these things just by the gravitational wave signature that we get. It's that chirp that, because they're in the audio frequency range, it's amazing. So two black holes coming together go whoop, and the chirp itself is when they actually finally become a single object and stop emitting gravitational waves.
Right.
So it's the frequency goes up as the collision, as the collision takes place, and it's by analyzing the exact waveform, if you like, of that event, that you can get all the details, like the masses of the objects, the orbits that they were in, their spin. All of these things come out of the analysis, and that was what made GW190521 unusual, because two things that there were three things about it that were weird. One is that the black holes were more massive than were expected before. I can't remember what their masses were, but in terms of the mass of what we call stellar mass black holes, the ones that probably originate from the collapse of a massive star, they go up to 20, 30 solar masses tops. And I can't remember what the two in GW190521 were, but I think they were a bit heavier than that. But also there was basically a flash of radiation as well. I'm not sure where that observation comes from, but it's not usual for these black hole mergers to produce a flash of light, but this one did.
Wow.
But the really weird thing, and it might not, to us perhaps it doesn't seem all that weird. The two black holes that were merging as they spun together, they were in orbits around their common center of mass. That's how these things work. But the orbits were highly elliptical. They were very elongated.
Oh.
Whereas all the others have been circular. The orbits have been circular, and that's why. That's because I might actually just read a bit. This again comes from phys.org. Great place to get astronomy news.
Website.
And it's from one of the professors at the University of Florida, one of the institutions that contributed to this work. So here it comes. The gravitational wave event GW190521 is the most surprising discovery to date. The black hole's masses and spins were already surprising, but even more surprising was that they appeared not to have a circular orbit leading up to the merger. And that is because the fundamental nature of the gravitational waves emitted by black holes, which doesn't just bring the pair of black holes closer for them to finally merge, but also acts to circularize their orbits. That's actually a different professor at Columbia University. And once again, yes, this is all from a press release from Copenhagen, just to give all the acknowledgements. So that the bottom line there is that normally when black holes merge, the physics of what's happening actually makes their orbit circular. But in this case, it didn't. And so that's why this is such an interesting piece of research. And another quote, if I may, it's great to have the quotes from the original scientists in this work. This is Johan Zamsing in Copenhagen. It made me start thinking about such non-circular mergers can happen with the surprisingly high probability, as the observation suggests. That's the high probability comes about, I guess, because, you know, if you say there's been 90 mergers, there's actually been fewer black hole mergers. The 90 is the total number of gravitational wave events we've seen. In that number, to get one in 90 that's non-circular is a high probability. It doesn't sound that high. You might expect it to be 1 in a million or something like that, but it's you know, of the order of 1 in 100. And so the answer that they've come up with is that what's happening here is we've got black hole collisions, stellar mass black hole collisions happening within the accretion disk of a supermassive black hole at the center of a galaxy.
Oh.
So what you've got is a supermassive black hole. We know this happens in the centers probably of most galaxies. And sometimes those things are really, you know, they're very energetic, and so you get material emitted at the poles of the black hole. We talked about that a couple of weeks ago, the one that was inclined. Actually, I might just mention, if I may digress for 1 minute.
Sure. Very unlike you, Fred.
Jeff from Avalon, a person I know well, phoned me up and said, you said that, what was it? That the angle of tilt of this black hole, this is the one we talked about, I think 3 or 4 weeks ago, Andrew, was more acute than Uranus, which sort of, you know, had undertones that I hadn't realized when I said those words. So,
you know, I picked up on it too, and I let that one go through.
You didn't. Well, I missed it altogether. I do apologize for that.
That's okay. That just shows that you've got a lot more integrity than the rest of us.
I'm trying to work out what I'm going to say next. Put my foot in my mouth each time. Anyway, so normally, you know, with a supermassive black hole that's gobbling up its surroundings, you get these jets of material that are usually perpendicular to the disk, the accretion disk, and they, you know, they become radio galaxies, very bright, sometimes quasars in the early universe. Our galaxy is a bit quieter than that, but it probably still has at least some sort of accretion disk going on around it, because we occasionally see infrared flashes from the galactic center here in our own galaxy. Anyway, the bottom line is that the idea that's come from this research is that because this disk of swirling material has got higher velocity and density than its surroundings, it suggests that the stellar mass black holes that might form within that environment, they just, the quote is from Benti Koskis, I think is the way it's pronounced, from the University of Oxford. In these environments, the typical velocity and density of black holes is so high that smaller black holes bounce around as in a giant game of billiards, and wide circular binaries cannot exist. So that's why, you know, the thing is so elongated. And I think it's also possible that that's the environment that would have given rise to the flash that was seen. It's because it's in a disk of material, and so you've got this huge sudden input of gravitational energy into it, and that probably explains the emission of light coming from the gas around it.
Yeah, I can only see one big problem with the theory, Fred.
I knew you'd pick a hole in it, Andrew.
Yeah, billiard balls are traditionally red.
There's one black one though.
Oh, that's snooker.
Oh yeah,
Billiards is a different game. No
Yeah.
pockets.
Of course, yes. Billiards is only red.
Yeah,
That's correct. Yes.
there you go.
Well, maybe it should have been that. I think you should write in, Andrew.
Well, we can just change the name of them to red holes, and we're covered.
Yeah, no, it's the analogy. It should be a game of snooker, not a game of billiards.
That's a good point.
Yes.
That's a very good
Anyway,
point.
it's very nice that something that has been a puzzle for actually since 2019 when it was observed seems to have been perhaps laid to rest now, which is great.
Yeah, and it also puts into play a potential question as to whether or not this is very common.
Yes, that's right.
Could this be happening at the center of our galaxy?
It could be. We haven't seen, a gravitational wave signal from black hole mergers in the center of our galaxy. That will be quite a shake. But it could potentially happen. I think that's correct.
Wow. So when you say quite a shake, what does that mean?
No, we're not going to feel the Earth move. And let me just add to that.
That never happens, Fred.
I'm not going to go there. I won't touch that one. The disk of material around our galactic center is pretty rarefied because we can actually see, with telescopes like the European Southern Observatory's very large telescope down there in Chile, they observe stars going in orbit around the black hole. And a year or so ago, there was a gas cloud that was seen approaching the black hole, which they expected to get torn to pieces, but it didn't. So the disk is, I think, fairly rarefied. It's not like some of these active black holes where there's huge amounts of material whizzing around it. I think ours is fairly gentle. So there might not be black holes. I think there are thought to be black holes in the environment of the supermassive black hole at the center, smaller ones.
Yeah.
But I don't think there's anything, there's nothing that yet in terms of a merger. But it could crop up anytime. That's the thing about these things; they just pop up.
We live in calmer waters, perhaps.
A nice way, a nice turn of phrase.
Perhaps, yes. We'll see. If I wake up in the middle of the night because the Earth moved, I'll know what it was. Okay.
I'll leave that one with you.
Moving right along. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Okay. I got a note from Hugh saying that the live feed is working brilliantly and we have people watching. I'm scared now.
Yes, I am too.
Because we're going to try, this was just a test on YouTube, but we're going to try on the live show to just punch it out to every platform we're on. So we'll go live everywhere.
Yeah, it'd be great.
Maybe.
Maybe.
I think it'll be terrific. Okay, question time. Now, because we can't get the audio to play through that pesky interface, we're going to do it the hard way. Now, question one was that one there. All right, I'm good. I am ready to go.
Very good, Andrew.
Yes.
It's never been in dispute.
I didn't mean that good. I mean, good to go. All right, here we go. In 3, 2, 1. Push the button, Andrew.
Zero G, and I feel fine.
Space Nuts.
And I'd like to send a shout out to all our social media followers because there are lots of them, particularly on YouTube, where our numbers have been climbing steadily. And it's good to know that YouTube is getting behind podcasts because that'll be good for everybody who puts podcasts on YouTube. So they've seen that that's an opportunity for them, and that's good for everyone. So thank you, YouTube. Also Facebook, where we've got 2 pages there. We've got the Space Nuts official Facebook page and the Space Nuts podcast group. The second was created by the audience so that they could talk to each other. So it's a great place to get together and talk astronomy and space science. And I particularly love the way those backyard astronomers show each other their pictures, which I think is fantastic. And some of them are awesome. Some of them are amazing. And of course, Twitter, we're on, Instagram, we're on, whatever your personal choice, we are there, except for some of the more weird ones. Don't go. We don't like weird. We like weird in astronomy. We don't like weird in social media. Anyway, so thank you for following us, and certainly feel free to join any of our social media platforms. Now, we've got some questions, Fred, and the first one comes from Simon.
Hi team, Simon from Newcastle. Thanks for the great podcast, really enjoy it. My question is around the formation of life, the formation of elements and the Fermi paradox. So my understanding is that in a normal star, a star will only form elements up to iron, and that after that we need other processes to form elements above iron in the periodic table. And that I believe, not sure, that might be when it goes supernova. So then Fermi paradox states, where is everyone? Well, I was thinking maybe an answer to that could be that life itself might require elements that are higher up the periodic table than are normally produced in a standard star cycle, and that perhaps we actually need supernovas, and that in itself would then lead itself down to the conclusion that perhaps we are one of the first, even though Earth's only 4 billion years old, universe is 13 billion years old. Maybe we did actually need that period of time to get to this point. Anyway, would just like to know if that actually adds up and makes sense. Thanks for your time.
Thank you, Simon. Very astute and a really interesting question. Can you elaborate a bit, just to start with, on the Thermi paradox? He did refer to what it
Enrico Fermi's famous postulate from, I think, 1960 or thereabouts. Where is everybody?
Yeah.
Because it's really applying the Copernican principle to us as living organisms. And the Copernican principle is that there's nothing special about where we are in space and who we are. And it's named after Copernicus because he took the Earth from the center of the solar system, which people thought it was before, and said, no, it's just, it's just a planet.
It's just a rock. And
it's a rock.
Third rock
from the sun. Yeah, that's right.
In fact, didn't we talk some time ago about how our part of the universe is actually really boring?
Well, that could be part of the reason why we're here, because boring's good when you're trying to evolve living organisms. But yeah, so Fermi's argument was if there's nothing special about us, and the universe is 13.8 billion years old, they didn't know that back then, but that's the sort of, still knew it was pretty old. Why haven't species formed earlier than ours? And why haven't they colonized the whole galaxy, basically? Because even if it takes 60,000 years to get from one star to another, as it would in our case to get from here to Proxima Centauri, over a long enough time span, you could do that. And even if it was colonized by robots, so-called von Neumann machines that could self-replicate, we should have evidence that there is intelligent life elsewhere. That's the Fermi paradox, and we haven't, and we still haven't. 62 years later, we still haven't.
We're still looking for it on Earth.
Yes, that's right. Now, Simon's argument's a good one, but the issue though is that supernovae, which he's absolutely right, they're the source of many of the heavier elements than iron, that and things like neutron star mergers and things of that sort, which creates some of the heaviest elements. Gold, for example, comes from them. They started happening probably within the first 100 million years of the universe's existence. So for almost the whole age of the universe, what you might call the interstellar medium, the space between stars, has been enriched with these heavier elements.
Okay.
And in fact, that's how we date stars in terms of how old they are. It's by the number of how much of the chemical elements is in their atmospheres. So a star like the sun, its atmosphere is rich in all the, I can't remember the number, it's 60 or 70 different elements which are in the sun's atmosphere. Might even be more than that. And it's essentially a highly enriched cloud of gas that the sun formed from. But if you look at stars which are very, very old, and there are some, they've only got hydrogen and a little bit of iron in their spectrum, not much at all. But the bottom line is that right since the beginning, the enrichment of the raw materials of life has been taking place. So it doesn't actually explain the Fermi paradox. In fact, that's part of the Fermi paradox, that we know this has been going on for a long time. So, with the ingredients of life have been there for a long time. Why aren't we seeing it? And you've had my answer to this many times before, that the likelihood seems to be that step, we think microbial life might be common, might be reasonably something we might even know that within the next decade, Andrew. I hope we do. But higher life forms, even plants, may not exist anywhere else except here on Earth, or at least in our galaxy. Given the number of galaxies in the universe, 200 billion, it's probably it seems likely that there might be something in other galaxies, but the possibility is that we are it in our own galaxy, which is a phenomenal thought.
Yeah, it's hard to comprehend given the size and scope of the universe and all the situations that exist, that life couldn't exist somewhere else. You just got to look how life grabs hold in the most hostile environments on Earth. So it stands to reason that there's got to be some form of life beyond our planet, possibly even in our solar system.
Yeah.
But yeah, as you say, going from microbial to plant life is a giant leap. And then going from microbial to intelligent life is a massive leap. And I think you could put it down to the fact that the formula has to be right, the circumstances have to be right, the environment has to be right. All the things that created us have to exist somewhere else in some capacity for intelligent life to spawn. And, again, you probably would say, given the size of the universe, it's got to exist somewhere, but no evidence of it. And even if it does exist, we may never know about it because of the distances.
Yeah. I mean, a big step with this will come with the James Webb Space Telescope. Because one of the things that they're going to be doing is analyzing to death the atmospheres of exoplanets. As soon as something, CFCs or something like that turn up in one of those, then you've suddenly changed the whole name of the game.
Yeah. Unless it's some life form that's been created in a completely different circumstance.
I think astrobiologists are pretty open-minded about that. They look at all kinds of different chemical possibilities for creating life, ones that don't involve water at all. I mean, all life on Earth is water-based, but great question. Great question.
Thank you, Simon. Let's go to our next question, and this comes from Liz.
Hello, Lord Dunkley and Professor Watson. This is Liz from Florida, and I have a question about Mars. Now, this may be more of a sci-fi question, but nonetheless, we know that the core is dead on planet Mars. And as we know, without an active core, there is a lack of magnetic field, which will essentially not be able to sustain an atmosphere. Now, we can terraform an atmosphere all we want, but over time, that will essentially seep out through the cracks and there will be no more atmosphere. Now, is it possible to harvest the sun's energy? As we know, the planet gets radiated quite a bit. Is it possible to harvest that energy in, let's say, some kind of towers or something that can then send the shock down through the planet, down to the core, and recharge the core? So, kind of act as a planetary defibrillator. Thank you for your time.
Wow. I like the question. I like
Yeah,
the concept.
I do
Very
too.
sci-fi. In fact, they did make a movie called The Core because the core of the Earth was slowing down and threatening life on Earth as we know it. So they sent a crew down on a special drill ship to get to the core and fired nuclear charges into it to reignite it. So, yeah, that's
So
been done in sci-fi.
What happened, Andrew? What was the outcome of that?
Oh, they fixed it.
Oh, they fixed it, of course.
Spoiler alert.
yeah, spoiler alert. The planetary defibrillator. I love the idea.
Or Packer-Wacker, as we call them in Australia. I should probably now explain that.
You should.
Kerry Packer was a media magnate in Australia, very powerful, very rich man, Australia's richest man for a long time. Didn't take care of himself health-wise very well and had a heart attack one day. And the ambulance used a defibrillator to save his life. And he found out that there just weren't many of those.
Mm-hmm.
So he paid for every ambulance in New South Wales to have a defibrillator so that they could save people's lives like they saved him, which was a great thing.
Yeah.
And we affectionately referred to them as Packer-Wackers, as we do in this country. We give everything a nickname. So Packer-Wackers are what a defibrillator is.
That's fantastic. I think I knew about the principle, but I didn't know that's what they were called.
Yeah,
that's very good.
Packer-Wackers.
Yeah. Well, that's probably the most interesting part of the answer to this question.
Oh, Liz.
Yeah. Look, it is. Yeah, terraforming Mars it's not possible because it's not just the the lack of a magnetic field that stops you holding on to an atmosphere. It's the fact that the planet's too small. It's once again, it's connected with simply the gravitational pull that is needed to hold on to an atmosphere like ours, which Mars doesn't have. It clearly, at an early stage in its life, did have an atmosphere because we see evidence of water and that sort of thing. And it may well be that the magnetism then was high enough to stop it being eroded away by the solar wind and things of that sort. But it's always going to be, it's always going to be a negative answer to a long-lasting atmosphere like the Earth's because it just drifts off. It's not heavy enough. In fact, we see it happening. There's it's the Marvin spacecraft, a NASA spacecraft that actually watches atoms leaving Mars's atmosphere. There's several images that show different species of atoms drifting off, including carbon, the carbon dioxide, and oxygen and hydrogen.
Which makes Marvin paranoid. Think about that one.
Yes, I like that.
Yeah.
I wish I could think of things like that. Anyway, never mind. So stirring up the core, if you could do it, and I think the answer to that is there's no known physical method that would let you do that. What you'd have to do is heat it up so that it became more liquid. There may be a bit of liquidity there now, but there's not enough to create a dynamo to generate the magnetic field.
Yes, it's possibly done a piston engine thing and seized at this stage.
Seized, that's right, yeah. In which case, unseizing it needn't necessarily start it spinning again. So you might still wind up with no magnetic field, even if you nuked it to boil it up a bit. So my answer to all that is to create artificial environments in space which you can control, and with mega engineering,
live in bubbles.
Yeah, that's right.
Yeah, there you are, Liz.
Thanks, Liz, for the question. That's a good one.
Thanks for the question. Probably beyond capability to fire up the core. But you never know. One day, in years to come, we might be able to harness the energy of the sun and do all sorts of weird and wonderful things. who knows? Finally, Fred, just to follow up to something we talked about recently. This is from Greg. Loved the show, Andrew. Only me. Fred, only me. Quick question about something we talked about recently. The good professor told us that the person sending their question was right, that light would slow down through a glass rod from the speed of light in a vacuum. But he missed the most important bit for me. The light will slow down, the energy loss will heat up the glass rod, but after exiting, will the light accelerate back to light speed in a vacuum? Yes. If so, where did the energy come from? Or is the clue in redshift? Energy is lost, changing the frequency, but still, how can it accelerate back to the speed of light in a vacuum? And I pondered that as well. I mean, if it's going at the speed of light, hits the glass rod and slows down, and then comes out the other side, how does it speed up again? Has it got P plates on it?
Yeah. Well, there isn't. Here's the thing. Light and P platers are quite different.
Yeah, light is slower. A P plater is a provisional driver.
Light might be slow, but yes, it is. But light doesn't accelerate. And we've had this. We had this question before.
I see where you're going.
Yeah,
okay.
It's created at the speed of light.
Yep.
So it doesn't accelerate, and it doesn't decelerate when it hits the glass. It is just traveling
through
more slowly
medium.
Through the other medium, and there's no energy loss. There is absorption, but that's not the kind of energy loss that we're talking about. That's that's like light passing through a plate of glass will be absorbed to some extent, and that basically heats up the glass.
So as far as the light's concerned, it's traveling at the speed of light.
Yes.
Regardless, and the glass is just a minor infraction.
That's right. It doesn't know that it's actually inside glass. It's still traveling at the speed of light, but the physics is that the glass is slower. Has a high refractive index, so
yeah,
the light is slowed down. So there's no acceleration and no energy loss because of that, or energy gain. However, Greg is right. Sorry, Greg, I forgot your name there for a minute. Seeing it on my screen. Greg. Now. Yes, it's still Greg. And I'm still forgetting names. Never mind. You're right that if one way of... you're right that when photons lose energy, their spectrum is redshifted. That's correct. That's what happens in terms of energy loss. But this is not an energy loss because it's still traveling at the speed of light. So doesn't apply.
There you go. All right. Hope that helps, Greg. Thanks so much for your follow-up question. We don't mind people asking questions about questions because quite often in astronomy, questions do create more questions when we give you a half an answer. So appreciate it. Thanks to everyone who contributed to this episode. Now, if you do have questions for us, don't forget you can send them to us a couple of ways via our website. There's a little tab on the right-hand side that says send us your voice message. That's a good way. There's the AMA tab where you can also send voice questions or voice messages, as well as the old-fashioned email system. And plenty of other things you can do on our website while you're there. You can visit the shop where you can buy a shirt with that logo on it, or you can buy the tote bag there, or the up there. So that's the mug. There's all sorts of stuff on our in our shop. If you and Fred's latest book and his old books, the ones he wrote with Galileo, are in there too. Plenty of stuff in the shop. There's a membership button. I don't know what that does because I'm already a member, so I've never pushed it, but you can check that out as well. spacenutspodcast.com or spacenuts.io if you want to visit our website. And that wraps it up for another week. Fred, thank you so much.
Great pleasure, Andrew. Always good to talk, especially live.
Yeah, it was fun, wasn't it?
Yeah, it's good.
Felt the same as doing it the other way.
Yes.
With a few more bells and whistles.
Yeah.
But we'll catch you in a week or so. Thanks, Fred.
That's great. See you soon.
See ya. Fred Watson, astronomer at large, joining us every week on Space Nuts. And thank you for joining us as well. Great to have your company. Keep those cards and letters rolling in. And we look forward to your company next time. From me, Andrew Dunkley, bye-bye for now.
Space Nuts.
You've been listening to the Space Nuts podcast.
Fleet Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.
And that should end the live show. Thanks for watching, those who found us. We'll talk to you soon.
Yeah, that's right. Good on you.